Hello, my name is Ron Patrick. I'm with ECM. This video is the tutorial for ECM's Lambda sensor calibration system. The Lambda sensor calibration system is for Lambda sensors used with ECM's analyzers and modules. The sensors used in these analyzers and modules have a memory chip in the Lambda sensors connector. In this memory chip is stored ECM's factory calibration and your field calibration. Once the sensor is calibrated, the calibration goes into the memory chip and is used wherever the sensor is plugged in. By putting the calibration into the connector, these sensors can be calibrated in a central location and distributed to where they will be used. This allows you to maintain remarkable traceability and consistency in your Lambda measurements throughout a large facility. The system consists of a rolling cart with a Lambda can kit, a Baro can kit, a remote display, a sensor simulator in the drawer, and a PC running ECM's configuration software. You plug the cart into the wall, turn on the switch in the bottom here, attach the sensor, and follow the procedure. Now a little background on the Lambda sensor. The Lambda sensor operates on the diffusion principle. As such, you can calibrate it in a single gas. Air is the easiest to use. Due to the sensor design, there is no zero drift, but there can be a span drift, so the calibration simply consists of a span in air, which we call span O2. I'll go through the procedure to use the calibration system by following what's written here. Number 1, switch on power bus on lower shelf. Soon the remote display is going to power up. Then press the on button on the PC. It'll take about 30 seconds for the PC to start and to start our configuration tool software automatically. The software is also located here on the desktop with the two manuals, one for the Lambda can and one for the Baro can. Should come up any second. There's our configuration tool. Click on Modules and then Start. You'll see initializing node 20 and 10. 20 is the Baro can, 10 is the Lambda can. Then you connect the sensor to the Lambda can cable and hang it in stationary air, your cal gas, pointing down. And this tray with the fingers allows you to put the sensor at different heights. Some sensors have longer cables than others. The sensor is going to get hot, so be careful. In 1 minute, the sensor will be close to its proper temperature. Now, if you're in a room where there's a lot of wind, there's not going to be stationary air, and due to thermal reasons, the O2 numbers are going to jump around. So in the case where you have a lot of wind, take a clean can and just put the sensor in it like this. It'll quiet down the effect of the wind. We don't have any wind in here, so I'm going to take this off. After 1 minute, after the sensor's up to temp, read in the bottom corner the error code, which here is 0x00, which means the sensor is okay. If you don't get a 0x00, it means the sensor is broken and cannot be used. Error codes are described on page 14 of the ECM module configuration software manual, which is right here on the desktop. Now you have to wait for 1 hour until the number stabilizes. For a new sensor, the number will stabilize in about 1 hour. For sensors that are used, it might take longer because you're evaporating condensed fuel or oil or water that's inside the sensor, and the sensor is not seeing pure air. For the case of sensors that are used in the intake manifold of engines, for example for our EGR meter, you might have to wait 24 or up to 48 hours until the number will stabilize. Stabilizing means that it's plus or minus 0.03% O2 over a couple minutes. It'll diddle up and diddle down a little bit. All right, let's assume that an hour has passed. Note that the displayed O2 for the sensor is less than the actual O2. This is common. Typically when a sensor ages, the span goes down and this number will be less. Now let's do the calibration process. Select the module 0x10, that's the Lambda CAN module. From task, select span O2. You're going to open up two windows. One says displayed O2, the other one says actual O2. The displayed O2 is on the upper part of the display. It's the O2 displayed by the Lambda CAN with that sensor attached. The actual O2 is the right answer. So what we're going to do is type in the displayed O2 here, 20.20 and 20.73. Okay, let's change it to 19. And then we'll change to 20. Okay, 19. And then you click span. What it does is it performs a span on this sensor using air of a known composition 20.73 and then downloads it into the memory chip. And you'll see it's off a little bit. It's hard to get it dead on because the sensor is going up and down and the sensor hasn't been warmed up for 1 hour. But within 0.03% O2 is good enough. For stoichiometric engines, anomaly stoichiometric engines, gasoline engines, an error of 0.03 in this calibration is negligible air-fuel ratio. It's 0.00000 way out there in the decimal points. For a diesel engine at 50 to 1, that's lean when it's idling. An error of 0.03 will be about an air-fuel ratio of 0.14. After the calibration, you're going to get an age factor. If a sensor is new, the age factor is 1. As the sensor ages, the number will go down. We recommend that when the age factor gets to 0.8, that the sensor isn't used any longer. If you mess up the spanning, you can reset the span, and the age factor will pop back to 1, and then you can repeat it again. You can span and reset a sensor as many times as you want. Now the sensor is approximately matching the actual O2, well within the O3 requirement, so you can disconnect it. When you disconnect it, you're going to get an error code. It'll go 14. 14 means open heater or sensor disconnected. But anyhow, the sensor has been calibrated, and you can distribute it to the test site where it can be used. Now let me talk about the traceability of the calibration. The Lambda sensor is a device that measures a gas composition and outputs this composition via an output current. Thus the calibration of the sensor requires an accurate knowledge of the composition of the span gas and the ability to accurately measure the sensor's output current. The span gas we're using, air, is 20.945% O2 minus the amount displaced by humidity. And that's no matter where you are in the world. So the calibration depends on how accurately you can measure the humidity displacing the air. With the ECM calibration system, humidity is measured by the BaroCAN module, which uses two sensors, a humidity/temperature sensor and a pressure sensor. Math is then performed in the BaroCan module, resulting in a percentage O2 in air that is displayed on the lower display. This number should be 20.945 if there was no humidity in this room. Typically, you'll see a 20.7 number. The sensors used by the BaroCan are calibrated by ECM, have a calibration tag on them, and can be periodically sent back to ECM for recalibration. The ability for the system to accurately measure current is verified by the sensor simulator, which is a precision current and voltage source. Here is a sensor simulator. I'm going to demonstrate the use of the sensor simulator to verify that this Lambda can is properly measuring currents output by the Lambda sensor and by voltage outputs from the pressure sensor, which performs a pressure compensation. This is a precision current and voltage source, and you can send this back to us once a year to have it calibrated with these three sensors. You don't have to check out the Lambda can very often. I suggest once a month with this system. To check it out, it's really simple. You just pull out this connector and plug it in and follow the instructions on the bottom of the device. Okay. You have to look on the PC. So this device outputs 4 currents, simulating 4 different stoichiometries with the sensor, and 4 pressures. So click it on to rich Lambda, which here it says should output minus 2.02 milliamps of IP1X. That's the fundamental current coming out of the sensor, is called IP1X. So you look down here at the parameter, IP1X, it says minus 2.023. I want 2.022. It's plus or minus 1/100th of a milliamp. It's within spec. Then you repeat it for stoichiometric, which is for 0 milliamps. Lean, which is 0.956 milliamps. Air, this is simulating a 6 milliamp NTK sensor, should be 6 milliamps in air. And the displayed current output from the Lambda can should be the same from this precision current source. To simulate pressure outputs, its voltage, you have 4 voltages. The first one is less than 5 millivolts, and that is called PVLT, the pressure voltage. This thing is 8 millivolts. Then you go up to 1.267. It's a little bit of averaging going on here. Okay, it's coming in. 1.266. It's within spec. And you have 2 more voltages to go through. Once the Lambda can has passed this test, you know that it can accurately measure the currents and voltages from the Lambda sensor and the pressure sensor. Like I said, you don't have to do this part very often. Once a month is good enough. So, to maintain and verify the calibration of the sensor calibration system, you send these 2 sensors for the BaroCan back to us with the pressure sensor and the sensor simulator. It's recommended that you do this once a year. Also, we recommend once a year that you replace this Lambda cable, because after repetitive insertions, you might wear the gold off the terminals and cause a voltage drop inside the connector. It's easy to replace this cable. I hope this short video has allowed you to quickly come up to speed in using the Lambda sensor calibration system. If you have any questions, please call ECM.